Hello, this is Roberto Carlos Gaitán Reyes, and this is evidence 2, state feedback in discrete time for design of control systems. I will start by explaining what is a discrete time state space model. This model involves several components that define the relationship between input and output data of a space-time system. Based on the following example, some main elements can be defined. As we can see, the function p of x is the value of the discrete state. X is the sample time at the desired time in position -1. A, B, C, and D are the dimensions of the state space matrix according to the number input given, and U is a continuous input signal. To sum up, a state space model uses state variables to describe a system by a set of first-order differential equations, and it's the best option for quick estimations. In this other example, we can see that t is the sample time, u of kt is the input at instant kt, and y of kt is the output at instant kt. When all system data like inputs and outputs are sensed and displayed in some point of the control system, providing useful information, this is known like the state feedback with observer. This type of system are useful to identify responses and frequencies where correcting automatically, which is a solution when we need to be sure about every single aspect of the system configuration to predict the development of the system, avoiding any risk of an incorrect function of the model. One of the things we have to consider when implementing a state feedback controller with observer is that if we want the estimated state to converge with the real state, the system must be observable and controllable. In MATLAB, we have two functions that we can help us to implement this type of controller. One of these is the Ackermann method, which takes as an input the phi and the gamma matrix of the model in state space of the system, as well as the poles we want to place. The second function called place is based on numeric methods and occupies the same inputs as the Acker function. Both functions are used to obtain both the gain vector L and the vector K, but we must consider that for the vector K, the input matrices must be transposed. For the choice of the poles we want, we have to recap on some basic rules for pole placement. The S-complex plane is a representation of sinusoidal exponential components in a given function. By representing the root of the transfer functions in a graphic way, we are able to obtain the poles and zeros, useful to describe the dynamic behavior. In order to achieve the conditions required, we will need to translate the S-plane to a C-plane from our system using the C-transform. Whilst using the reload provided by MATLAB, we ensure that our poles and zeros for our previous defined criteria is marked in the correct region of the body diagram. Finally, we have to design and modify a state feedback controller with observer for a gravity crane in order to achieve the following goals when controlling it. The closed loop system must be stable, meaning that all poles must be within the unitary circle. The bandwidth of the closed loop system should be at least 0.2 rads per second. The settling time should be less than 30 seconds, and finally, the input signal should not exceed 40 kilonewtons. First of all, in order to get the right values of the poles, we need to obtain the matrix results from the PCMap function. After this, we might obtain the desire of an estimation of the poles that we will implement in the PD matrix value. In these simulations, we run with the data above in PD. Implementing the matrix value in PD, we will need to modify it in order to obtain the best possible outputs of the system. As we have seen in this simulation, the pole zero map, the poles and the zeros obtained must stay within the unitary circle. In order to do this, both the real and the imaginary values must be modified. Finally, with the poles we decide, we have to interpret the graphic so we can see if we comply with the requirements. First, we determine if the bandwidth of the closed loop system is at least 0.2 rads per second at the body plot graphics. As we can see in the top left graphic, at the moment the magnitude is -3 dB, where the bandwidth is observed, the value is bigger than 0.2 rads per second. Now, for the settling time of the system, according to tau in second-order system, about 99.8% is considered a good system response. As we can see in the graphic presented, both linear and non-linear outputs show that its settling time is less than 30 seconds. Lastly, the maximum force applied to the trolley is about 16 kilonewtons for the nonlinear model, and for the linear model is less than 14 kilonewtons, sorry, which confirms us that the system complies with all given specifications. To conclude, in this subject, as its name implies, I have learned from the most elementary to complex subjects about control systems, which is one of the most important themes for our careers as mechatronic engineers. Before these 10 weeks, I knew very little about control and its implications in the industries. However, at the end of this period, I have realized that control is a fundamental part in the training of any mechatronic, and also it is highly used in practically in all industrial automation networks. Besides this, now I feel able to develop and control system in different ways or with different tools, such as PID. And now I feel capable of interpreting the results of the graph in order to improve the process developed more and more. Thank you very much.